Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on numerical integration and how to implement it in Java. In the past lectures, we discussed the basic idea of integration, which was the definition based on the Riemann sum. And the Riemann sum is basically partitioning the interval and then evaluating the function at some point in the interval and multiplying by the delta x, the length of the interval. And we said that as if the function is Riemann integrable, then this series must converge to a value regardless of which point you choose inside each partition. We discussed the rectangle estimation of the integral, the forward estimation, backward estimation, and the center. And we said that rectangle estimation gives the exact result. For a finite number of sub-intervals, the rectangle estimation gives the exact result for constant functions. And we also said that the center approximation is generally better than the forward and backward because of the fact that if we take the center, then there are some portion of the rectangle that are outside or that are outside the area below the curve, and there are some part that is not inside the rectangle, and these two can compensate for each other. And then we said that if we want to rigorously calculate the series, the Riemann series, basically we calculate the Riemann sum and then let the number of partitions, which is n here, goes to infinity. Then we need to be able to calculate the exact, or at least the order of magnitude of some summation from 1 to n, for example. And typically we end up with the 0th order, k to the 0th power, k to the 1 power, k to the second, and k to the third. And the approach that I presented was the difference sum. And the basic property is that if I take a sequence AK, right, and try to sum from m to n over the difference of two consecutive terms of this sequence, AK plus 1 minus AK. If you expand this and explicitly write it, you see that all the terms cancel out except for the last term, which is you put the last index inside the one that has k plus 1 index. You end up with an plus 1 minus the first index, which is am, right? And then we said that in order to calculate all these sums, k squared, k cubed, we use this property that if I want to calculate the k to the p power, I set the ak in the difference equation to k to the p plus 1 power. And then we use the recursion. So k to the 0 power gives me the constant summation, the sigma over constant. And if I put it here, I immediately end up with this, the constant number times n minus n plus 1, which is the order of n, right? If n goes to a very large number. And the recursion happens because for k squared, we have to use k cubed here in the difference, and k plus 1 cubed gives us some terms such as k squared, k, and constant. So we use these and then we calculate k cubed. And the general property was that the sum of k to the sum m power, or k to the p, sum of k to the p when n goes to infinity is equivalent to k to the p, k to the basically p plus 1 over p plus 1. This is the order of magnitude, all right? And then I gave some examples on how to go ahead and calculate the exact integration by using the limit of the Riemann sum. And again, we don't need to calculate the exact summation. We just, if the integral is, the function is integrable, we just need to calculate the order of magnitudes. The exact summation based on n gives us also the error term, and we discussed that. And we said that for the rectangle approximation, the error is linear, which is not good, because if I want to reduce the error by one order of magnitude, I have to actually increase the number of intervals by one order of magnitude, which is not good. And then we discussed two properties of the integral, one, and they both directly come from the summation property, the property of summing a couple of numbers. One is the linearity. So f plus lambda g is f plus lambda integral of g. So integral of f plus lambda integral of g. And that's based on the condition that both f and g have integrals in the a to b interval. And the other one that is kind of important is the breakpoint property. So I can, if the f is integrable, I can break the integral of f from a to b to to the integral of f from a to c plus from c to b. And c doesn't even have to be inside the interval of a, b, right? C could be anywhere as long as these two integrals are available, all right? And that's a very important property. And in order to kind of understand it, you can just look at the case when f of x is a constant function. Then the result is f times b minus a. Here we have f c minus a plus b minus c. So when we sum b minus c plus c minus a, regardless of where c is, whether c is greater than a, less than a, whatever, b minus c plus c minus a always gives you b minus a, right? And then we also looked at the integration of polynomials x, which had an antiderivative of x squared over 2 from a to b, x squared, which was x cubed over 3. And then we said that in general, for any polynomial x to the mth power, the antiderivative is x to the m plus 1 over m plus 1 when you calculate from a to b. So polynomials are always integrable. And actually polynomials are a very important thing, as we discuss later, that in terms of numerically estimating the value of the integral. All right. Now the next thing that we discussed was implementing the integration in Java, and we defined a interface to define a real valued function as the integral function. And then we passed that integral function or integral function 1D, because later we will expand to 2D and 3D. We will extend to that. And then we passed this integral function object to an integral 1D. So the class that we defined that actually performs the integration is integral 1D. And then we said that, okay, we implement the rectangle or any type of numerical approximation, and our stop criteria was basically the number of sub-intervals, how many times we sum. And we could also later implement the convergence criteria instead of having a hard stop criteria in terms of the number of terms. Now I mentioned that we can use the built-in function interface in the Java library to implement this interface. So let's quickly head to Eclipse to discuss that. I have my demo integral project here, and in the integral 1D, if you recall, we had this constructor that we passed the integral function 1D. Now here I'm passing a function which is a built-in interface in the java.util.function package, all right? And it's annotated by functional interface. So it's enforcing that this has to be a functional interface. And if we go inside this, see, it's in the runtime util function in the function package, all right? It's a functional interface. It's a parameterized, it has a type, input type, and a return type R. So we typically use the function apply, passing the input type, and it returns a type. And we can also define the composition of two functions, and then identity function, for example. And as you can see, it's designed to be used with lambda expressions because this is a functional interface. And what I'm doing here is that I pass a function which takes an input of double and returns a double, right? But then in order to be consistent with the rest of the code, I just converted to my integral function 1D, right? So this sort of conversion which makes it convenient not to deal with different types of interface when I write the code. So when I'm writing all these methods, I want to deal only with one interface, which is my integral function 1D. But because most programmers might already know about this function interface in Java language, it's good to have this capability, right, for the constructor to accept that. So here I use a lambda expression to convert to this integral function 1D, which is also a functional interface. So I get this function and call the apply method. Remember, it returns a double object, right? If I pass in a double, first of all, if I'm using the property of auto boxing and auto unboxing. If you don't know what these are, you can go back and review some of my early lectures on the operator overloading. So basically the idea is that we can use the double primitive and the double object interchangeably, and the compiler is smart enough to convert them. So compiler is smart enough to handle it. And this was the basic idea of operator overloading. And this double class has a method called double value, which I'm using here. And whenever you use a double in place of a double object, the compiler can do that. Now the problem is that this function is supposed to return a primitive type, not a double object. That's why I'm calling this dot double value on the function. Otherwise you will get an error, because then the compiler says, okay, I really can't do anything about the fact that I'm returning a double object, and the double object I can't do this kind of multiplication with a double number, because there is no type conversion here. Okay, so you have to call this double value here, and then in the test integral, if you see here in test 3, I already created this. Okay, in test 1, if you see now, first I define an integral function 1D, which is a constant t goes to 1, and then I call the forward rectangular approximation to integrate it from 0 to 4. And then I'll define a function interface, double t returns a. So the thing is that if I remember, this function has to return a double object. So if I return, for example, 1 here, let's turn this to 1. This will give me an error. Actually it doesn't, it works, because it automatically does the boxing and unboxing. Now as you can see, I'm passing this function 1, which is a functional interface. Now if I don't call this double value, let's see what happens. So basically here now the return type of this interface, a lambda expression, is a double object, not a double primitive. It still works. And so that's also good to have. But let's say we say 2t, for example, here. Instead of constant, we try 2t. Let's see what happens. Still works. Both of them work fine. So everything works fine here. And you can use this. Most of the times, if you're dealing with a one-dimensional real function, you can use this built-in function interface. There is also a 2D version of it, which is called the by function, but right now we're just using this function interface. All right. And then when we progress in the calculation, numerical calculation, we also talked about the trapezoid method, and we said that the idea of trapezoid method is to enhance the idea of rectangular approximation. And we said that, okay, in each sub-interval, instead of instead of approximating the function with a constant function, we approximate it with a linear function, right? Consider a linear approximation of it. And that means that the trapezoid method always gives an exact result for any linear function. If my f of x is a linear function, when we approximate it with a linear function in each interval, we actually approximate it with itself, right? And then we said that then instead of summing f of xi times delta x, the area in each subinterval is f of xi plus f of xi plus 1 over 2 delta x. And we sum over this, all right, from 0 to infinity. And this enhances the error, the order of magnitude of the error. So the rectangle was a linear error, but the trapezoid was squared, second order, which is a better enhancement, which is a good enhancement. And but we didn't implement it in Java, so let's head to Java and try to implement it. So if I go to integral 1D, remember this is the class that implements all the integration. So public double trapezoid, and again double start, double end, and basically in terms, or terms is basically the number of some sub-intervals. So what I'm going to do, and then yeah, obviously we have the similar things here. We define our delta, and again the idea here is that we're doing a uniform partitioning. That's the idea for now. We will see how to extend this to non-uniform partitions, because in fact non-uniform partition in most cases is a better choice. It gives us a better order of magnitude for the error. Now in each subinterval, instead of summing delta times the value of the function at the center here, I'm going to, so the first thing I'm going to do, I'm going to create an array of funcvals, new double terms. So how many times do we need to calculate the function value? So if you recall, let's say we have 1, 2, 3 subintervals, right? Our term variable is 3. Then I need to calculate at here, here. So terms plus 1, right? So terms plus 1. And then for int I equals 0, I less than terms plus 1, I plus 1 us. What I'm going to do, I'm going to funcvals I equals func dot value at basically start plus I delta. Okay, so first I evaluate the function at all the points that I need, and then here what I'm going to do to implement the trapezoid is that, okay, sum equal plus equal delta times funcvals funcvals of I plus funcvals of I plus 1 divided by 2 or multiplied by half. All right, and this is the sum, this is the trapezoid. Now why did I create an array of the values? So why did I do this first? Because if I directly call the value method in the on the function, then I'm evaluating the function at each point twice, which is not good, right? I want to evaluate the function at all the points that I need to evaluate only once, and then use those calculated values. Now if the function is a simple function, it's not a complicated one, then it doesn't make that much difference. But if the evaluation of the function has a huge cost, then it's better to do this. Then we save some overhead, right? Let me go back to the slide and show you what I mean. So if I directly call the function in my summation, then let's say in this interval, I calculate the function at a and xi. And then in the next interval, I calculated f at xi again. So I'm calling the value method on the f function at xi twice, which is not good, right? So that's why I'm evaluating the function only once, get all the values of the function, and then do the trapezoid estimation. So let's go back to our test cases. So we had this test 3. Now let's call it test 4. In the test 4, also I'm going to call test 4. So in the test 4, we have this t squared, and from 0 to 4, and then we call the forward approximation, backward, center. Now let's also call trapezoid. Integral finder, trapezoid, start and 100 terms, trapezoid approximation, and then let's also look at the error. Trapezoid error is result trapezoid minus exact. So forward, backward trapezoid 21.3328, and the exact is 21.333. So we have so the center approximation was 21.3328. And the trapezoid is also 21.3328. So as we can see, the center approximation and the trapezoid approximation give basically the same error. Okay? And that's because they have the same order of magnitude error. Now let's go to t cubed, and then the exact, I have to multiply this, the exact becomes n to the 4th power minus start to the 4th power divided by 4. So center approximation 63.9968, the trapezoid approximation 63.9968. And you might wonder why these two are always giving us the pretty much the same result. That's because when you have so many terms, a linear approximation is a good approximation of this type of polynomials. And the exact result here is 64. So the forward and backward have a large error, but the center and trapezoid are pretty accurate, and the center is more efficient in terms that in terms of the fact that we're only calculating the values of the function once. But using the trick that we use for the trapezoid, and the fact that okay, we're also calculating the values of the function only once, then these two are basically, in this case, they have almost exactly the same performance in terms of the evaluations of the function. So my recommendation is to always go with the trapezoid. All right. Okay, so this is a trapezoid, and maybe let's try to test other functions. For example, t sine of t, and we don't have any closed form exact result, so let's just compare them. Why do we have error? Okay, so we have to call math.sine. forward 1.9178, 1.7967, and center and trapezoid, as you can see, they're giving us exactly the same result. Okay, but again, to reiterate, the main difference here is that for the center rectangular approximation, we evaluate the function at the center of each subinterval, right? For trapezoid, we evaluate the average of the function, basically at the beginning and the end of the interval, and we calculate the average and then multiply it by delta x, all right? And both have the delta squared error, the quadratic error, which is good, gives us a faster convergence. I think I made them. Okay, yes. So I was looking at the. Yes. So sorry, that's my mistake. I'm looking at the. I was looking at the result center also for trapezoid. So let's run this one more time. And then maybe let's go back to t squared and try to look at the, or maybe t cubed, because we already have it. So we have result for the forward, result backward, result center, and result trapezoid. So trapezoid, now we see that the trapezoid has actually pretty much the same error as it's not that much different in terms of order of magnitude. So trapezoid and the center are relatively accurate. So let's go back to t squared. End cubed minus start cubed over 3 is the exact result. And in this case, exact is 21.333, and then both of the center and the trapezoid gives us, both of them give us very accurate results. All right, but my recommendation is to try to always use trapezoid instead of center. All right, so the next thing is that as you can probably see, we have been following a pattern, and the pattern was that we tried to approximate the function in each subinterval with a polynomial, right? The rectangle was a constant polynomial, which is basically just a number, constant number. So it's a 0th degree polynomial. The trapezoid was a 1st degree polynomial, right? Now it is just intuitive to try to basically go on with this approach. So Simpsons method is basically saying that, okay, in each subinterval, approximate the function with a 2nd degree polynomial or a quadratic polynomial. Now the question is, why would this work? And the reason is Taylor series. And we briefly discussed Taylor series when we discussed polynomials. So the idea of Taylor series is that if we have a function that is very well behaved, it doesn't have a crazy infinite discontinuity or something, and that's pretty much the condition for Riemann integrable. So the function, if the function is continuous and it has integral, then we should be able to expand, do the Taylor expansion, right? The idea here is that if the interval is the subinterval is small enough, we can expand the function as a Taylor series, right? A Taylor polynomial. And as we increase the order of that Taylor expansion, the degree of that polynomial, better and better we approximate the function. And then I mentioned this idea that, okay, if the interval is small enough, and if I come up with an approximation, f sub approximation for the function, then these two integrals should be pretty close enough, right? We can, instead of directly calculating the integral of the function in a small interval, we calculate the integral of the approximating function, the f of approximation, right? F sub approximation. But the key here is that we choose this approximating function wisely in a clever way so that we can actually calculate exactly this integral. And which is the function that always has an exact integral is a polynomial. No matter what these coefficients are, we can always exactly calculate the integral from a to b, right? That's why we like polynomial and use polynomials to implement the rectangle, trapezoid, Simpsons, or whatever. So if I consider this approximating function as a Taylor expansion, quadratic, in each subinterval, let's say it's just one interval a and b, and it's very small. Then if I approximate the function with a quadratic polynomial and put it in the integral, I get this. So if the integral a and if the interval ab is small enough so that this approximation with a quadratic polynomial is accurate enough, then the integral is approximately b minus a, which is the length of the interval, over 6 times f of a, so the value of the function at the beginning of the interval, plus 4f of m. M refers to the midpoint of the interval, which is a plus b over 2, plus f of b, the value of the function at the endpoint. And you can see the error is delta to the 4th power. So we jumped from trapezoid, which was delta squared, to delta 4th, which is a huge enhancement, right? But the price that we are paying is that we need to evaluate the function at 3 points in each subinterval. So if I have n subintervals, if I have n partitions, then I have n evaluations for the function at the beginning of end of each point, also n other evaluations at the midpoint of each interval. So the number of evaluations doubles. So that's the price that I'm paying. But the order of error goes by a factor of 4. The order of magnitude is 2 orders of magnitude higher than the trapezoid. So if the evaluation of the function doesn't have much cost, it's easy to evaluate it, it's better to go with Simpson because it gives us much faster convergence and small error. But if evaluating of the function gives us higher cost, numerical cost, then it's better to stick with trapezoid and go with the trapezoid, right? Because the order of magnitude error is smaller, but we might get a faster performance because the number of evaluations is less. All right. So this is the basic of Simpsons method. In the next lecture, I'm going to implement this in Java. Thank you for watching, and I'll see you in the next video.